Welcome to International Biorenewables Law and Policy. This presentation is part 3 of our 3-part series on algal biofuels and aviation biofuels. In this presentation, we'll talk about some of the biofuels that are specifically being targeted for meeting some of the demands of aviation energy consumption. To give you some context, the aviation industry consumes 1.5 billion barrels of Jet A1 fuel per year. Even though humans don't take as many trips through airlines as they do by vehicles, we still produce a majority or a significant portion of our CO2 from each flight that we take. As you can see here, flights produced 705 million tons of CO2 in 2013. The majority of those emissions are from long trips, international trips. Part of the reason that the airline industry is interested in biofuels is that we could reduce aviation emissions by more than 80% with the right types of biofuels, and we'll dig a little bit deeper into this number. The aviation industry contributes about 12% of the total transportation emissions and about 2% of total man-made emissions on the planet. It's not an industry. The aviation industry is one that is expected to grow in the coming years. So what you see here are global traffic growth rate forecasts, which range between 5 and 8% per year. The notion here is that consumers are expected to continue to take more and more flights. Particularly international flights are expected to grow significantly in the years 2014 to 2019. There are several policies that are either in place or have been under heavy consideration that prompted the aviation industry to take a strong look into reducing their emissions. The main one is one by the European Union, where they established an emissions trading scheme that was required for any flights that were either within the European Union or into or out of the European Union. Essentially, if you were flying a plane or you had an airline that flew planes into the European Union, you will be charged for parts of your CO2 emissions. This trading scheme was initially discussed in 2012. There was a moratorium placed in actually implementing the trading scheme until the International Civil Aviation Organization meeting slated to take place in 2016. So there is a little bit of a holding pattern, but airlines know that there is a charge that's coming, and so they're taking a proactive view reducing their emissions. In the United States, the Environmental Protection Agency made some statements that they would look at the transportation industry next in terms of what emissions they contribute. But as of 2016, they had not have implemented any specific policies targeting aviation biofuels. So the types of targets that the aviation industry is looking at include not just meeting some of the mandates that governments are considering, but actually looking at the potential for negative emissions by 2050, or by reducing their emission levels to less than 50% of their current emissions. What this schematic shows is that based on the growth rates that are expected, if they made no actions, you would see that emissions relative to 2005 levels would be expected to increase. If they move towards carbon neutral growth, they would be able to sustain those levels up to 2050. But by including advances in technologies, operations, infrastructure, and in particular the adoption of biofuels, they believe that they can reduce their emissions to half of the emission levels in 2010 by 2050. A lot of these emissions, or achieving these emissions, will depend on getting China on board. The bulk of emissions coming up from the present to 2020 are expected to be generated from airlines and trips associated with China. The US is going to see some growth, and so is the European Union. But as you can tell from this graph, they're both dwarfed by the emissions coming from China. That a lot of the biofuel production would come from energy crops. These are your lignocellulosic biomass like miscanthus and switchgrass and energy sorghum. These are dedicated crops, so new crops that are currently not being planted but that could be planted. Um, and that will be followed by crop residues such as corn stover and forest residues and byproducts. But they still believe that a significant portion of the jet fuel should be produced from algae, particularly because of what we've discussed earlier, which is you can grow a large amount of algae in relatively small pieces of land very near airports and thus be able to provide biofuels reliably and cheaply. And so when they did their scenarios, they looked at what are the biomass resources that are located within 100 miles of the major airports in the United States. And so based on those airports, they estimated how many barrels of jet fuel and kerosene could be provided to those airports. And as you can imagine, this is you don't just need to be near an airport, you need to be near a biomass resource, and then you need to be near a refinery facility that can convert the biomass into a jet fuel that's acceptable to consumers and that meets the tight specifications required for airplanes. And so in order to meet those tight specifications, there are several companies and startups that are on their different stages of meeting the required approvals. So if you look at jet fuels from biomass and renewable oils, you need to get ASTM approval before they would even be considered. Some of the pathways that are being developed include hydroprocessing and Fischer-Tropsch synthesis, but there are also other pathways, novel pathways like alcohols to jet, catalytic oil to jet, sugars to jet, and fermentation of sugars to jet. Obviously, the conventional approach is to simply use crude oil and hydroprocess it into producing jet fuel. Of these technologies, hydroprocessing is one that's already commercially available. The Fischer-Tropsch and alcohols to jet are certified, but as of 2016, there were no commercial examples of these technologies. And then there are the novel technologies that are being developed are currently under pilot testing. There are other technologies that are still at the lab scale, not shown on this graph. To give you an idea of some of the people or developers that are working on these technology, gasification in Fischer-Tropsch has been studied by the National Renewable Energy Laboratory here at Iowa State. We've published some studies on this topic. Hydroprocessing, certainly Pacific Northwest National Lab, or PNNL, has developed this technology significantly. And there are several studies in this area that you can find in some of our references from the course. To give you an idea of what it typically takes to convert algae, for example, into gasoline and diesel, you can look at this study by our research group where we took algae without the oil. The oils have been removed from this algae, and the algae can be converted into biocrude using hydrothermal liquefaction. That biocrude can eventually be upgraded into gasoline and diesel. Now, with aviation, we have to be a little bit careful and have to understand how carbon numbers play into this role. When you do hydroprocessing, what you get is a mixture of hydrocarbons with different carbon numbers. Gasoline or naphtha is typically on the lower range, anywhere from C4 to C12. Diesel is typically on the higher range, starting from around C10 to C24. Jet fuel is a mixture of hydrocarbons that are in between that range, from C8 to C16. And typically, to meet the ASTM standards, you have to have a certain mixture of those C8 to C16 carbons. Just like the study by the Berkeley group, we looked at the production cost of jet fuel, of biofuel production from algae. What is shown here are the cost of the fuel in dollars per cubic meter. What's most important to note here is that, again, capital costs are a significant portion, almost half of the cost compared to the operating cost. If you look at the cost by process area, this doesn't include the growth of the algae. We're just looking at the conversion step. Uh, the biomass itself is expensive, and the hydrothermal liquefaction or final upgrading and finishing of the product is expensive as well. Now, yes, the cost of producing jet fuels is expensive today. You can see all the different factors laid out here by the National Renewable Energy Laboratory. This is similar to what we found in our studies. In order to meet the price of jet fuel, we're going to have to reduce costs across the board, but particularly in the cost of producing the feedstock. That remains the major cost component of producing aviation fuels. One item that's particularly different of the aviation market is that the cost of jet and diesel is relatively stable when you compare it to the overall cost of the energy market. And so on the left side here, we have the price per gallon in 2010 to 2008 to 2012 of gasoline, diesel, and other types of oils. And then on the right, we have just the cost of jet and diesel prices. And so this different trends of the feedstock price and the market price of the fuel are important to consider because economically it can be challenging to predict how well your facility is going to operate when you have these two different sources of uncertainty, which, as we have seen, contribute a significant fraction of the cost of the biofuel. We've mentioned that biofuels have the potential of reducing carbon emissions by 80%. This graph here shows a comparison of the different ways in which that can be accomplished. On the left side, you have conventional crude oil, which has emissions close to 100 grams of CO2 per megajoule. Oil sands, certainly more polluting. The crude mix is somewhere in between. As you move towards pyrolysis, you're below 40 grams of CO2 per megajoule. And the further you go, Fischer-Tropsch jets, if you use coal, you're going to perform worse than crude oil. Natural gas is also more polluting than crude oil. But if you add carbon capture and sequestration, you can reduce that margin quite a bit, but you still remain at a higher emission levels than conventional crude. Using biomass to Fischer-Tropsch, you can reduce your emissions to about 10 grams of CO2 per megajoule, which is, again, below that, is greater than 80% reduction in emissions. With algae and soybean oils, because the conversion step is fairly straightforward, you can see that your emission levels are also relatively low in the 20 to 30 grams of CO2 per megajoule. So in summary, what we've learned is that the aviation industry has established some aggressive targets to reduce their overall emissions by 2050. There are several types of biomass that can be converted into aviation fuels that meet the ASTM standards and expectations of consumers and the industry. However, although there are biofuels that can help reduce aviation emissions, the cost of producing these fuels remain high relative to fossil-based alternatives. This is going to be a continuing narrative with many of the different markets for biofuel production. And so we'll eventually look at some of the ways in which we can make biofuels more competitive. But for the aviation industry, it is going to be the emission requirements that will drive adoption of biofuels.